In this lecture, we learn how to use volumetric glassware and how to calibrate them. We know that for volumetric analysis, we use pipette to deliver accurate fixed volume called aliquot, burette to deliver accurate but variable volume called tide, and volumetric flask to prepare standard because it contains accurate fixed volume. Sometimes we also use the volumetric flask to prepare our sample. From the three diagrams we see here, volumetric flask has long, narrow neck with a ring to indicate the calibration mark. The calibration was done by manufacturer for the accuracy of up to 0.2% for B class and 0.1% for A class. A class glassware comes with calibration certificate, and A class must be used for precise, accurate measurements. The calibration procedure must be done in accordance with the functionality of the glassware, delivering or containing the liquid. The type of pipette we use for our volumetric analysis deliver a certain amount of liquid. So this type is called single volume pipette or bowl pipette. In this particular example, this pipette is to deliver 25 milliliter of liquid, and this is the nominal volume printed on the pipette. There is also the error limit calibrated by the manufacturer, that is plus and minus 0.03 milliliter for this particular pipette. The type of the pipette also engraved on the pipette. So this one is an A class. Sometimes you may also see the letter S next to A. S stands for swift delivery. Information about the calibration must also be given on the pipette. For this particular one, it was calibrated at 20 degrees Celsius. It has 5-second waiting time. Waiting time is the time started from when the minuscule stopped moving. So for this particular pipette, you wait for 5 seconds before you take the pipette away from the receiving container. The calibration of this pipette was done to deliver a certain amount of volume. So you see the code on the pipette is TD to deliver, or sometimes EX. The glassware should also have the ISO number. ISO stands for the International Organization for Standardization. If the glassware is made in Germany, it will have the DIN number. DIN stands for Deutsche Institut für Normung, the German Institute for Standardization. You may also see the code EN, that stands for European Standard. On the pipette, you would also see the manufacturer mark and the country of origin. Sometimes you may see 4 digits written on it. This for the year and the batch number. When you use the pipette, you must never draw the liquid past these marks. And to choose the pipette to use, you should look for the one with long pointed end. This is more reproducible. Regarding burette, the information given on the burette should include the nominated volume. In this case, it is 50 milliliter. The precision of the burette. So in this case, it is plus and minus 0.05 milliliter. It should also show the graduation interval. In this case, it is 0.1 milliliter. So this means between the line here is 0.1 milliliter. For A class burette, you see the complete circle at the whole number here, and sometimes you see a blue line in the burette to help with the accurate reading of the meniscus. Burette often has no waiting time. If there is waiting time, it should be written on the burette or in the certificate. The good burette would also come with long pointed tip. For volumetric flask, the information for the calibration, you see IN, or sometimes you see TC, stands for calibrate to contain. The additional information you see is the NS number. This is the size for the stopper. The volumetric flask opening here have a little bit like a cone shape. So it have to have a perfect fit stopper. It is quite hard to read the bottom of the meniscus. A trick is that if we put a black card behind the glassware below the graduation mark, then you can see better the bottom of the meniscus. Why volumetric glassware is calibrated at 20 degrees Celsius? First of all, we know that the volumes of liquids and gases vary with temperature. For example, 1.0000 gram of water occupies 1.0018 milliliter at 20 degrees Celsius. That volume is expanded to 1.0044 milliliter at 30 degrees Celsius. Therefore, the calibration of volumetric glassware must be done by weighing the calibration substance at non-temperature. By convention, manufacturers calibrate volumetric glassware with distilled water at 20 degrees Celsius. For accurate measurements, volumetric glassware must be calibrated in the laboratory environment where the measurements will be carried out. The calibration substance is a liquid, so we must pay attention to density and viscosity of the liquid. And because we weigh the liquid, so buoyancy must also be considered. We need to know the density of the calibration substance accurately because we use it to convert from the mass of the liquid to the volume of the glassware. And obviously, we need to know accurately the temperature of the liquid when it is being used for the calibration. Viscosity has some effect on the volume delivered when the liquid is drained from the glassware. We know that the higher the viscosity, the more liquid remains in the pipette or burette. So this means that the delivered volume is less than nominated value. So this systematic error can be corrected or included in the calibration if the calibration substance have similar viscosity to the sample. So this means that having similar viscosity, the amount of liquid remain in the pipette or burette will be the same for both substances, the calibration substance or the sample. In this unit, we use dilute aqueous solutions. So distilled water is used as calibration substance. We know that air exerts different buoyant forces on the steel or brass mass in the balance and the object being weighed. The object being weighed is the water or the solution. We can correct the mass of the object using the equation below. You don't need to remember this formula, but you must know how to use it. In general, all analytical chemistry textbooks will give you the conversion factor for the volume occupied by 1 gram of water weight in air against stainless steel weight in the balance. So this table is from the textbook. This factor including the correction for density and buoyancy. So if you calibrate your glassware at 18 degrees Celsius, then you use this factor to calculate the true volume of your glassware. The third column in this table is corrected to 20 degrees Celsius. If you do an experiment over a long period of time, the temperature in the lab vary. So if you convert all your calibration to 20 degrees Celsius, then you can compare and use the same, say, standard solution. Say, for example, if you prepare your standard solution at 28 degrees Celsius, a summer day in the lab, you convert it to the volume, it should be at 20 degrees Celsius. You calculate your concentration accordingly. Then in a winter day, in the lab, the temperature is 12 degrees Celsius. You convert your calibration to 20 degrees Celsius. Then you can use the standard that you made in the summer day for the determination of your sample in your winter day. To calibrate a glassware is actually to determine the true volumes of the liquid, either contained in or delivered from the glassware, and the reproducibility of that true volume. Class B glassware can be used for high precision accurate work after being calibrated. And the glassware calibration is done by weighing by difference. This means that the exact weight of the water in the container is a difference in the weight of the container before and after water is added to the container. And we must know the temperature at that time. To avoid evaporation, a stopper must be used. It should only be opened when the water is being added to the container. Let's have a look at how to calibrate a volumetric flask. It is important for us to remember that volumetric flask is used to contain the liquid. So we must know how much liquid it is in the volumetric flask. The procedure starts with weighing a clean and dry volumetric flask with the stopper on. Then we remove the stopper. We add distilled water into the volumetric flask until the bottom of the meniscus touches the calibration mark. Put the stopper back on. Weigh the flask. The difference between the weight in this step and the weight in the first step is the exact weight of water in the flask. So this is our first reading. Then we empty and dry the flask. When the flask is completely dry, then we repeat the process from step 1 again. We need to get at least 3 weights of water in the flask. 5 is better. It is important to remember that we must use a clean and dry flask for each time we do the calibration, for each reading of the calibration. For the pipette and burette, we want to know the volume delivered from the pipette or burette. So we do not have to use dry pipette and burette. So in general, the calibration procedure for volumetric flask can be used for pipette and burette, but step 4 can be removed. And if the container, the receiving container have too much water, we can tip some water out, dry the outside of the flask, and do the weigh for step 1. The pipette and burette is to deliver the liquid. So we need to have consistent waiting time for the calibration and for the use of the pipette. For example, if you decide to use 5-second waiting time, you give 5-second waiting time for the calibration and every time you use the pipette. Now let's have a look at the data that we have for the calibration of a burette. Let's go over the procedure of how to calibrate a burette. So first of all, we take the temperature of the water. Then we weigh the receiving container with stopper on, step 1. And then we deliver 50 ml of water from the burette into the receiving container. We take the weight. That is the third step of the procedure. The difference in the weight from the third step and the first step is the mass of the water in the first delivery. Then we deliver another 50 milliliter into the container. So the weight between after the water's added and the weight before the water's added is the mass of the water delivered the second time from the burette. If the receiving flask is pretty full now, you can pour out some water from it, dry the outside of the flask, put the stopper on, take the weight of it, and then deliver another 50 ml from the burette into it. Then take the weight and calculate the mass for your third delivery, and so on. So for 5 readings, then we do the average for these 5 readings. We determine the standard deviation. There are 2 types of standard deviation: population standard deviation or sample standard deviation. We use the sample standard deviation. So if you use Excel, it is std.ev.s. Then we also calculate the percentage or relative error. We use a standard deviation times 100 and divided by the average. Then we use the volume correction factor from table 2.3 for 19 degrees Celsius, because our temperature here is 18.8. With the correction factor and the average, we can determine the volume delivered by our burette. It is here 49.97 milliliter plus and minus 0.07 percentage. 0.07 standard deviation. So the true volume that we have is 49.97 milliliter. If we use the nominated volume of 50 milliliter, we would have 0.06% error just for the use of the burette. Remember, for accurate work, we have to have fairly small overall error. Sometimes we may have a number that looks different from the rest of the data. We have to ask ourselves whether we should keep this data or to reject it. So we can use the Q test to determine whether to keep or to reject the outlier. Depends on the percentage confidence we use. We can use different values here. Now let's have an example of a calibration of a 50 ml burette. We have this number 49.5576 different from the rest of the number. So we want to know whether we keep this data or we got to remove it. So for the Q test, first of all, we arrange the number from minimum to maximum. So this number, all these 5, we arrange from minimum to maximum. So we have here 5 data. And then we look for the difference from the minimum to the maximum. So this means our case, the difference between the maximum of 49.9425 and the minimum value of 49.5576. That is our W. Then we've got to determine the difference from the outlier and the value closest to it. So in our case, the outlier we're thinking of is 49.5576. The number next to it is 49.7863. So we find the difference between these two, and we find the ratio Q equal to D divided by W. Now we compare this experimental Q to the theoretical Q critical, and we want to know it at 95% confidence. We have here in total of 5 observations. So we use 5 observations at 95% confidence. Then we get this number 0.710. So our experimental Q 0.5942 is smaller than the Q critical at 95% confidence. So we keep this outlier. Of course, when it's bigger, when the Q is bigger than Q critical, then we have to reject the number.